Okay, so in the Zoom session today, my plan is to go over the atomic theory worksheet that's posted in the chapter 8 folder. And the material here, I mentioned this in the chapter note recordings where I went through the chapter notes and sort of my mini lectures that I did. I posted that yesterday. Um, this chapter for me was always sort of like, I don't know how to explain it. It was just kind of like, number one, it's a lot of historical theory perspective on how the atomic structure came to be. So in that sense, it's really interesting. But the way that they present the quantum mechanic model of the atomic structure, and then in the next chapter do electron configurations, to me, that kind of seemed strange. Like quantum mechanics to me is a little bit more abstract. I don't have the physics brain, I have the chemistry brain. So physics to me was always a little bit more like, I don't know, abstract, I guess is the word. And so you have the physics stuff here, and then you get into what I feel like is more practical, more chemistry, I guess, in the next chapter. So it just seemed weird to me that they're disconnected. So a lot of times what you'll find in the lecture videos that I recorded, I feel like I'm constantly referring to electron configurations that we did in intro chem. So I'm like, hey, remember doing this in intro chem, the s, p, d, and f orbitals? Remember that? And it seems kind of weird to do that because if you didn't have intro chem, your answer is going to be like, no, I don't remember doing that. So I never understand why it's presented this way. I understand to kind of give the historical perspective, but to me, it should be one chapter. Like, okay, here's the historical Einstein, Schrodinger, right? All the geniuses that came up with atomic structure and all their theories. And this is the application of it. Like, this is how it works. This is why we know it was so genius, right? This because it matches what our periodic table tells us, and it matches the behavior we expect for families of elements and charges and all. Anyway, so I think as a student, it's not that I struggled with this because there's a lot. It's just mathematical formulas, so in that sense, it's actually kind of easier. You just have to have your formulas and your constants, and then you're good. But I guess I struggled with it only because to me, it just seemed like it was, I don't know, like a way out there. And then it didn't really tie in the way I wanted it to. And I see how it ties in, but it's not until the next chapter. So that to me, it's just like kind of, I don't know, not weird. I don't know. I should write my own book, I guess, one of these days. So the atomic theory worksheet starts out with some formulas that are given here. So C, I talk about this in the lecture video. C is the speed of light. It is a constant of 3 times 10 to the 8 meters per second, which I put here, right? So that's your C. Lambda, that nice Greek symbol, that is your wavelength. And then your nu, sort of the curvy V, that's definitely not the right term for that, but that's what I call it. That is your frequency. And so what we kind of get into here is what is an electron, right? Does it act like a wave? Does it travel in a wave? Is it in a straight line? Is it a particle? Is it, like what is it? And so a lot of the theories behind this, like Einstein came up with photon, right? Photon is a particle of light. And so a lot of this ties into photons. So you'll see that term quite a bit. And it's trying to tie in, hey, electrons can act like those light particles. They also act differently, but we're going to compare them to those light particles when we do this sort of beginning atomic structure. And so when you keep seeing that term photon, that's just a particle of light. And again, we're going to start there and then see how the electrons also can kind of follow a lot of those same behaviors. So the first thing is that when we look at this, the wave nature of light, I think that's actually how it's referred to, is that as we know, light sometimes falls into the visible spectrum, right, where we can see it. It's a red color or a blue color, whatever it is. And the difference in color is due to the difference in the wavelength of the light. And in your book, this I always remembered was one of my favorite parts of the chapter. You have your electromagnetic spectrum. You can Google it if that's easier, because you always get basically right around the same thing. And so you've got like your high energy, high frequency waves, gamma rays, X-rays, ultraviolet. We know those are bad for us, right? They're damaging. And then we've got our visible spectrum, right, which they blew up here. There's the rainbow, Roy G. Biv, easy to remember. And then at lower frequency or higher wavelength, right, we've got past the red, we have infrared, and then microwave and radio waves. And of course, radio waves are everywhere. So thankfully, they're not damaging. So I always rate, you know, like the frequency versus the wavelength. I got to talk about that first. So when we talk about light and how it travels, and this is something I talk about in the video as well, the overall speed, regardless of the color, is the same. So one particle of light could be traveling like that, right? Where you look at this wavelength, which is peak to peak, right? Wavelength is pretty big. So let's say it has a large wavelength, which means it has a low frequency, right? Because those two are inversely related. Remember, wavelength times frequency is equal to a constant, 3 times 10 to the 8 meters per second. So if wavelength is high, frequency will be low. And then you can have a different wave pattern where you have high frequency and low wavelength. So again, your wavelength is peak to peak, right? So something like that. So this one, we have much lower wavelength, but this is going to make it high frequency. And frequency, what is that? It's technically how I always thought about was cycles per second, like peak to peak. How many cycles per second are we doing? And the units there sometimes will be in hertz, which is per second. Sometimes you see it as just per second. But I kind of I want it to be something per second. So cycles per second seem to work for me. So what kind of makes sense to me here is that when you have low wavelength, right? These are short, fast waves, right? So high frequency overall, they're still traveling at the same overall speed as the high wavelength, low frequency, right? If we were to time those two waves from start to finish point, they would finish at the same time, start at the same time, finish at the same time. It's just that the top wave that I draw is going to have like a low energy. I kind of think of it like it's nice and smooth. It has a high wavelength, low cycles per second. To me, it's a bit more chill. That's a word that my daughter keeps using lately. And then at the wave below that, right, this is more high frequency, right, low wavelength, right? So cycles per second is much higher, right? The frequency is much higher. And this is going to have a much higher energy. We're going to see that in this formula here, which is energy of that light particle or the photon is equal to h, which is Planck's constant. Constants, don't worry about memorizing those. Those will be given times frequency. So frequency and energy are directly related. If frequency is high, energy is high. And to me, that made sense that if I've got this nice, slow, chill particle of light, not a lot of energy there, but if we're doing something, you know, with the low wavelength, high frequency, it just kind of made sense that that would be high energy. And when you look at your electromagnetic spectrum, that matches what we think, right? Like when we have the violet blue colors, right? These are lower in wavelength, which means they're higher in frequency. And when we go past that, we get to UV, right? And X-rays and gamma rays. And those are even higher in energy, higher in frequency, lower in wavelength, right? Because they're inversely related, but high energy. That's why they're damaging, right? They can do bad things through our DNA. Whereas if you look at the red, the 750, which is at the end of the visible spectrum, this is in nanometers or times 10 to the negative 9 meters. When you get past that, right, higher wavelength, right, if we look at the wavelength numbers, higher wavelength, but lower frequency, and then infrared, even lower frequency, microwave, and then radio waves, right? These are non-damaging. So it always made it easy for me to remember because infrared is on the side of red and then ultraviolet is on the side of violet. We know UV, we hear about that, right? It's on the weather every day in the summer. If you're going to the beach, the UV index kind of thing, we know those are really bad. So UV on the end of violet, right? Ultraviolet. And so that always made it easy to remember. Okay, well, UV, I know high energy, high frequency. So the violet is on the lower wavelength part of that 400 to 750 visible spectrum. All right, so that's the electromagnetic spectrum. That was one thing I always liked about this chapter. I always like it when it ties into something that you're familiar with, right? Like in your everyday life. Okay, so a lot of formulas for this chapter. So first thing we're going to start with is the relationship of wavelength and frequency. There's a few problems here that we'll talk about that. Then what we're going to do is tie in that concept that when you have high frequency, you have high energy, low frequency, low energy, H again, just a constant. And then what we're going to do is tie these kind of energy calculations to the behavior of electrons in atomic structure. So those are sort of the pieces of this chapter. And then at the very end of the chapter, there's quantum numbers. And that's the part where I was like, why aren't they doing this at the same time as the electron configurations? And you'll notice that that's the second video I posted for the chapter notes. And I feel like I'm constantly saying, hey, remember when we did this in intro? So hopefully everybody in here had intro and somewhat recently too. Anyway, so problem number one here, it says, what is the frequency in hertz? And hertz, again, that is just like cycles per second, but a lot of times they even leave out the cycles. They just say per second, which that always bothered me. What per second? Anyway, so what is the frequency in hertz of a blue light? So something in the visible spectrum, blue light, probably around 400, 450 nanometers or 450, I think. And we're given off from a mercury street lamp, which has a wavelength, oh, there it is, of 436 nanometers. Okay, so we've got our wavelength. So wavelength is our lambda. So that's 436 nanometers, which is, when we remember our prefixes, this is why I had you remember nano back in the first chapter. That's 436 times 10 to the negative 9 meters, because nano is 10 to the negative 9. I remember the double N's. That made it easy for me. And we want to know the frequency. So frequency is your nu, your curvy V, whatever you want to say. And the relationship between those two is the constant, the C, the speed of light. So if I know my speed of light constant, C constant, always 3 times 10 to the 8 meters per second, and I know my wavelength, I can solve for my nu just by taking C divided by my wavelength, right? So my constant for C, 3.00 times 10 to the 8 meters per second. And I'm going to divide that by my wavelength. This is why I converted it to meters, because I wanted that unit to cancel out. 436 times 10 to the negative 9 meters. All right. And so a lot of calculations for this particular chapter. So be prepared for all of our calculations for this one. All right. So keeping two sig figs, I've got 6.88 times 10 to the 14th cycles per second, or remember, hertz is the substitution there, which is, I don't know, kind of a nicer looking unit, even though hertz doesn't really seem like it tells you what it is. So take your pick. So cycles per second, sometimes again, just per second or hertz. All of those are kind of interchangeable. So there's your frequency. Let's go in the opposite direction for the second problem. We want to know the wavelength of a broadcast frequency, right? So like a radio wave of 100.5 megahertz. All right, so my frequency, my nu, is 100.5 megahertz. So we want to remember mega. Again, this is another reason why I had you remember this one. Because if you were wondering, why do we have more than we did in intro? This is why. Mega was 10 to the 6. All right, so I'll just keep it. It's not perfect scientific notation, but that's okay. So 100.5 times 10 to the 6 hertz. And again, that's the same as 100.5 times 10 to the 6 cycles per second, right? And it's going to look better that way when we go to cancel out our units. All right, and we want wavelength. So it's the same relationship with C, right? We're going to need our speed of light formula. All right, so we've got C is equal to lambda times nu. In this case, we know C, it's always the 3 times 10 to the 8, or sorry, yeah, no, that's right, 3 times 10 to the 8 meters per second. And we have our frequency, so now we got to solve for lambda. So just like we did for number one, we're going to take that speed of light, divide it by nu, and that'll give us our lambda. So 3 times 10 to the 8 meters per second divided by our frequency, 100.5 times 10 to the 6 per second. So now we can see how that unit of per seconds is going to cancel out. So 3 times 10 to the 8 divided by 100.5 times 10 to the 6. And I get here 2.9. Nope, I think I did that wrong. Hold on. Let me do that again. 3 times 10 to the 8 divided by 100.5 times 10 to the 6. Oh, no, that's right. Okay, so 2.99 meters. All right, so wavelength, quite large, right? So definitely not something in the visible spectrum. So wavelength is much larger. And if we go back up to that picture, right, back up here, comparing these two, right, we had 436 times 10 to the negative 9 meters versus 2.99 meters, right? Much higher wavelength, much lower frequency, right? Those two things are inversely related. So we got our wavelength for that radio wave, right? Now for number 3, I'm going to skip it because it's the same thing that we just did in number 1. We're given the wavelength, we're asked for the frequency. So same thing that you did for number 1. If we're looking for the frequency, we're going to take C divided by lambda. And just make sure, because your C constant is in meters, right, that 11.5 nanometers is 11.5 times 10 to the negative 9 meters, right? And that's our wavelength, or our lambda. Okay, so that's going to be just like number 1. When I look at number 4, now we're going to do the energy calculation. It says we want to know the energy of a photon of light that has a frequency, right? That's our nu, of 7.42 times 10 to the 14 per second. All right, and so this energy is equal to h nu. That's our formula whenever we're looking for the energy of a photon, right? So we have the frequency. What we talked about was high frequency is going to have high energy. And the only thing we need for this is Planck's constant. And remember, you're not going to memorize the Planck's constants. The constants, I don't know. I don't see the point in those constants being memorized. So those will be given. So Planck's constant, 6.63 times 10 to the negative 34 joules seconds. All right, my computer froze real quick. So since we have the frequency and we have Planck's constant, really all we have to do here is plug and chug. So again, this chapter is kind of nice. There's a lot of formulas. So 6.63 times 10 to the negative 34 joules seconds, and then times our new frequency, 7.42 times 10 to the 14 per second. So the units of seconds is going to cancel out. We're going to be left with joules, which is a unit we're familiar with energy. So 6.63 times 10 to the negative 34 times 7.42 times 10 to the 14. And I get an energy here of 4.92 times 10 to the negative 19 joules. And that's just for one photon of light. All right. And so, you know, it's just one particle of light. Because I know you're probably looking at that and being like, well, that's really not that much energy. But you'll see in some some exercises coming up that will look at that in a mole of photons or a mole of electrons, right? And then that gets a little bit more relevant, like one single photon of light, right? That's, yes, that energy value is pretty low. All right, so if we had high frequency, we're going to have higher energy. If we have low frequency, we're going to have lower energy. So you always want to remember that relationship. So on the next one, it says we've got, and my computer froze again, the laser in a CD player, which people don't use anymore, I'm sure. This was a relevant question. Produces light with a wavelength of 785 nanometers. All right, and we want to know the energy of that photon of light in kilojoules. All right, so the thing that's a little bit different here is that we're given the wavelength. All right, so we have wavelength of 785 nanometers, or 785 times 10 to the negative 9 meters. And we are looking for energy, all right? And we know energy is equal to h nu. All right, so what we're going to have to do first is get our nu from the speed of light, like we just did in some of the previous examples. And then once we know our frequency, we can calculate energy. So you can combine the two formulas together, right? So we have frequency is going to be found by taking the speed of light divided by lambda. And so you can do that up front. You can say, okay, well, I'll have E equals h nu, where nu is going to be the C over lambda. In the homework, what I did, I always did things piece by piece. I don't know why. I just did it that way. So like in the homework, you'll see I do this first. I go ahead and get frequency by taking that 3 times 10 to the 8 meters per second divided by the wavelength that was given. Now I know my frequency, and now I plug it in, multiplying it by Planck's constant. So I kind of do it in two pieces, but you can certainly just combine the two formulas together. And so again, frequency is what we want, but we have to get it by taking C divided by lambda. So that's what I plugged in for frequency. All right, so Planck's constant, 6.63 times 10 to the negative 34 joules seconds. Speed of light, 3 times 10 to the 8 meters per second. All right, and then dividing that by our lambda, 785 times 10 to the negative 9 meters. So my meters unit cancels out. I've got seconds per second, so seconds cancels out. Then the unit I'll be left with will be joules. So 6.63 times 10 to the negative 34 times 3 times 10 to the 8, and then divide that by 785 times 10 to the negative 9. And my energy is 2.53 times 10 to the negative 19 joules. So there's my energy of that light on the CD player. All right. So that one, we just had a little additional step because when it's asking you again for the energy of the photon, we know that this is our formula, E equals h nu. And they just gave us a little extra step here because instead of giving us frequency, they gave us the wavelength. So we knew that we're going to have to get frequency first using that speed of light equation. All right, so the next question says the minimum energy required to move an electron from a particular atom is 4.65 times 10 to the negative 19 joules. And we want to know the wavelength associated with that. So this is where it starts to turn into looking at atomic structure and electrons, and the formulas pretty much stay the same. We get extra formulas though looking at electrons. So electrons, they are stabilized by being in the atomic structure. The closer to the nucleus, the better, the more stabilizing it will be. But those electrons can be moved. We can excite them. We have to put energy into that. And the electron can be jumped up to a higher energy level. And it can also relax back down to what's called ground state. If you're going to excite the electron and move it away from the nucleus, that is destabilizing for the electron. So you will have to put energy in to make it do that. Remember, the closer to the nucleus, to that positive charge, the happier the electron will be. So if you're going to move the electron away from the nucleus, that is going to be an endothermic process. You're going to have to put energy in. But as the electron relaxes back down to ground state, to its normal home, closer to the nucleus, it will release energy because that's a stabilizing, happy feeling for the electron. And as it releases that energy can come out sometimes in the visible spectrum. And that light that's emitted is sometimes very colorful and beautiful. That's how fireworks come to be, right? We take different salts, metal compounds. We put a lot of energy in with, high energy type combustible materials. We excite those electrons to outer energy shells. And as those electrons relax back down, they emit energy and the energy comes out in the visible spectrum. So again, you look for little pieces in every chapter where you're like, oh, that's really cool. So that was the one I remember reading about and being like, okay, I like this chapter. At least I like that part of this chapter. So we're going to take 4.65 times 10 to the negative 19 joules, and we're going to put it into this atomic structure and we're going to move the electron. We're going to excite it. And we want to know the wavelength associated with that energy, that light. And so we're assuming this is a light energy rather than like a thermal energy like we looked at in the last chapter. So what I'm going to do is, this is my E value, right? There's my energy. And I'm looking for wavelength. And again, the only formula I really know of with E, right, is h nu. But I want to know wavelength, right? So kind of like the problem we had up here. What I can do is I can solve for my wavelength by taking C divided by nu. All right. So I'm going to first have to figure out what my nu is, because that I don't know just yet. So I've got my energy, 4.65 times 10 to the negative 19 joules. I'm going to divide that by H, Planck's constant, 6.63 times 10 to the negative 34 joules seconds, and that'll get me my frequency. So let me do that part first. 4.65 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34. And so my frequency is 7.01 times 10 to the 14 hertz or per second. Now, if I want to solve for my wavelength, I've got my C, 3 times 10 to the 8 meters per second, and then divide that by my nu, 7.01 times 10 to the 14 per second. All right, so the answer I get to that calculation, I get 4.28 times 10 to the negative 7 meters, or that would be 428 nanometers, because I would multiply it times 10 to the 9 and then just moving the decimal over 2 spots, right? 10 to the 7 would cancel it out, and then 2 more would give it to 428. All right, so that would be in the visible spectrum, so 428 nanometers. All right, now it asks for the wavelength, so we could have just left it in this, the 4.28 times 10 to the negative 7 meters. We didn't have to put it in nanometers unless it specifies. All right, so next one, Again, this is just looking at one little particle of light, right? We're just looking at one photon of energy, right? Energy is really small. So the next question, now tying it into like mole. All right, so Avogadro's number is going to come in here. So we have a laser that produces a red light with a wavelength of 632.8 nanometers. We want to know the energy in kilojoules of that 1 mole. All right. Oh, and you know what? Back on number 5 on this one, I forgot about that. It was specifying for kilojoules. Sorry about that. So just that's a real quick conversion, right? That if I had my joules and I want to go to kilojoules, we know that just like a kilogram is equal to 1,000 grams, 1 kilojoule, yeah, is equal to 1,000 joules. So this one right here, 2.53 times 10 to the negative 22, because I'm just dividing it by 10 to the third kilojoules. All right, sorry about that. I knew I was overlooking something. I got on a tangent. Okay, so for this one, a laser produces red light with the wavelength, right? So lambda of 632.8 nanometers. And we want to know the energy in kilojoules of 1 mole of the photon of light. So that's the thing that we're going to kind of hone in on. If we're looking at 1 mole, we're going to have to use Avogadro's number. And remember, Avogadro's number, 1 mole of whatever it was, in this case, we can say photons, is equal to 6.022 times 10 to the 23rd photons, right? If we were looking at atoms, 1 mole is 6.022 times 10 to the 23rd atoms. If it were molecules, then molecules. So if we're looking at photons, it'll work the same way. So the mole always represents 6.022 times 10 to the 23rd. All right, so we've got our wavelength this time, and we want to do energy. So kind of the backwards of what or reverse of what we did earlier. So if my wavelength is 632.8 nanometers, which is 632.8 times 10 to the negative 9 meters, then my speed of light divided by lambda will get me my frequency. So 3 times 10 to the 8 meters per second divided by 632.8 times 10 to the negative 9 meters. All right, so this will give me my frequency. So 3 times 10 to the 8 divided by 632.8 times 10 to the negative 9. So I get 4.74 times 10 to the negative, or sorry, 14, 10 to the positive 14 per second. So there's my frequency. All right, then if I do E equals H nu, okay, I'm running out of room. So I've got the 6.63 times 10 to the negative 34 times nu. I'm going to have to just squeeze that in. All right, where nu is the 4.74 times 10 to the 14. So I'm going to go ahead and have what I had in my calculator, the 4.74 times 10 to the 14, multiply that by 6.63 times 10 to the negative 34. All right, so my E is 3.14 times 10 to the negative 19 joules. All right, now remember that's per 1 photon. All right, and I want to have it in per mole. Okay, so, oh boy, I hope it, and my computer froze. All right, so I should have left more space for this particular problem. Okay, so this is per photon. All right, so if I come over here, let me do it this right here. If I have 3.14 times 10 to the negative 19 joules, but it's per photon. What I'm going to do is photon is in the denominator. So 6.022 times 10 to the 23rd photons per mole. All right, and that's what we want it in per mole. And then this one also wants it in kilojoules. So another real quick 1,000 joules is equal to a kilojoule. So after all of that, this will be my final answer. So I'm going to take the 3.14 times 10 to the negative 19, multiply it by Avogadro, 6.022 times 10 to the 23rd, and then divide that by 1,000. And what I get here is 189 kilojoules. All right, and that energy looks a bit more, I don't want to say relevant, but with thermo last chapter, right? That seems like an energy I understand, you know, like 189 kilojoules. We saw that with heat capacity questions or thermochemistry, looking at thermochemical equations, right? So to me, that's like, okay, that seems like a tangible amount of energy, not 10 to the negative 19 joules. But it's because we were dealing with just a particle. Right now we're looking at a mole of particles, and so that makes more sense. All right, then on the next one, it's going to be very similar. We've got energy, again, in kilojoule of mole, kilojoules per mole. So again, we're going to be focusing on the mole, and we're looking at photons with radio waves that have a frequency here. So since frequency is given, we're just going to do E equals h nu and then convert the units. We won't have to use the speed of light equation here because we didn't get wavelength. We went ahead and got frequency. So that one I think we can probably skip, because what I want to make sure and capture is atomic structure and moving electrons from one place in the atom to another. Right? I may have gone too quickly. So when you get to the next page on the worksheet, number 10, it's going to start asking you those kinds of questions. Okay, what happens when you move an electron from the first shell to the second shell? Or what happens when it goes from the second shell to the first shell? Those are going to be energy calculations that we're going to do now. And the formula that we need for these is back on the first page. It's this change in energy formula. And unfortunately, different books present it differently. And it's like there's not a consensus on this formula. It's very odd. But I see that a lot in Chem 2 formulas too. So you've got the constant 2.179 times 10 to the negative 18 joules. It's a positive, there's no negative. And then in the parentheses, it's 1 over the initial n squared minus 1 over the final n squared. Now, this textbook that we're using, TRO, and the one that I remember using, it's a negative 2.179 times 10 negative 18 joules rather than a positive. And then they switch the orders of the n. They do the final n first minus the initial. So just to be clear, I'm going to give you the one that's in TRO, right? Because that's the one that I use on the homework, and that's the one I think that's more consistent with the reading. So the two formulas are the same. The only thing that happened from one to one is they changed the sign for the constant, and then they flip the order of the n. And that makes sense with subtraction, that if you change the order, a positive would become a negative or a negative would become a positive. So that's the only difference there. But I'm going to use the one that's in TRO, right? So the one I put in the box, that's the one I'm going to use. And again, that's going to be provided. You don't need to memorize that formula, I don't think. I think we can live without it. Okay, now where is that coming from? So when you do the reading in the chapter, what part of the atomic theory is again, going back to that idea that electrons want to be close to the nucleus, right? But they need to be away from each other because electrons repel each other. So mathematically, they figured out that there must be these sort of discrete spaces where the electrons orbit the nucleus. And those are called the energy shells, right? So when we look at our atomic structure, let me go on the back of this page. When we look at our atomic structure, we have our nucleus in the center, and electrons can fit in the first shell, and then more in the second shell. And as the shell gets bigger, even more, right? And there has to be some sort of definite energy that an electron gets from being in that first shell. And that has to be a different amount of energy, stabilizing energy, than being in the second shell, right? Because the first shell is better than the second. So yes, there's an energy associated with being in the second shell, but not the same as being in the first. And same with the third shell. There's an energy associated with being in the third shell, but not as good as the second and not as good as the first. So there's these energies of each discrete space. And when we do these calculations, we're always looking at sort of a basic hydrogen atom. Because when I first learned this, I was thinking, oh, okay, those shells are sort of defined in space. They're set, right? And then you start to learn, no, they're not. Of course they're not, right? That as the nucleus fills with protons, as you have more electrons in the atomic structure, these shells are not set in space. It's a mathematical probability. But what happens is those shells flex, they move, right? Depending on how much positive is in the center, how many electrons are in the way. So these are not just sort of set in space. So you'll notice that language, like in all of the questions when we look at this, like in a hydrogen atom, and you might be like, well, why are we in a hydrogen atom? Can't we be in like a magnesium atom? And it's because the calculations would be slightly different. The energy associated with being in the first shell, the second shell, the third shell, those quantized values, right? Those are for the theoretical hydrogen atom. When you start putting in more protons and electrons with something like lead, it's not going to have the same energies, right, associated with it. So that's why you see that terminology of being in a hydrogen atom. So basically ignore that. You don't really need to know that. So what the chapter starts out talking about is, okay, there's an energy associated with being in the first shell. There's an energy associated with being in the second shell. All of these energies, you'll notice, are negative because it's a stabilizing energy. So you can think of it like an exothermic energy, that being in the atomic structure makes the electron happy. It's got a house to live in, right? That we all want that. Now, with the energy of transition, if I take an electron in the first shell and I go up to the third shell, that is not going to make the electron happy, right? Because it's going farther away from the nucleus. The nucleus is where it really wants to be as close to as possible because that's the positive charge it's attracted to. So when you move up in your energy shells, right? And so what happens is your N is increasing. N is called the principal quantum number. It is the shells. So N of 1 is the first shell, N of 2 is the second shell, N of 3 is the third shell. So if you're going to move up in energy shells, your N is increasing, you're moving away from the nucleus. All right, that change in energy is always going to be greater than 0. Right? You can again think of this as an endothermic process that you're going to have to put energy in to make that electron move away from the nucleus, because again, that will make it unhappy. If I go the opposite direction, if I go from 3 down to 1, so if I move down in energy levels, all right, so N is going to decrease. So like in this case, from 3 to 1. In this case, your change of energy is always going to be negative. It's going to be less than 0. This is an exothermic process. This is happy, right? That makes the electron very happy to go from a third shell to a first shell. That's like getting front row seats at a concert, right? Like that's going to be a good thing. You don't want to sit in the back. You want to sit close to the nucleus. So energy will be released as you move closer to the nucleus. So when you see that, you'll see when you do the calculation, I used to always just double check. Okay, which way did the electron go? Should it be positive or negative? It's really easy to forget a positive or a negative somewhere with these calculations. So just double check it at the end. Anyway, so that's what we're looking at next. And that's what that formula is going to help us do. So when it talks about this, negative 2.179 times 10 to negative 18 joules, that's just our constant. And then we have 1 over the final N squared, so where the electron ends up, minus 1 over the initial N squared, wherever the electron started from, whatever shell that was in. So like as an example, and it froze again. If we're going from shell 1 to shell 3, right? So we're moving away from the nucleus, doing this one here. My initial would be a 1. And my final would be a 3, right? I'm going from 1 to 3. So in my formula here, 1 over 3 squared would be 1 over 9 minus 1 over 1 squared, or just 1, right? So that's what we're plugging in here, the shell numbers from where we begin and where we go. All right. So on that last page, we're going to look at some of these calculations. So for problem number 10, it says, what is the energy change, right? And so we know we're looking at delta E, right? Change in energy involved with when a hydrogen electron, again, don't worry about the hydrogen, falls from the 6th shell to the first shell. So that means my initial N is I'm going to start at 6 and I'm going to go all the way to the first shell, right? So intuitively, when I think about this electron going from the 6th shell, right, far away from the nucleus, all the way down to the first shell, which is right next to the nucleus, that's going to make this electron really happy. So we expect delta E in this case to be less than 0. This should be an exothermic process. Energy should be released. The electron is relaxing to ground state. I always kind of, like in my mind, I picture the electron like breathing out a big sigh. Again, I don't know why I personify chemistry so much, but apparently I do. So we're going to go initial shell of 6 to a final shell of 1. So our formula, right, delta E is going to be negative 2.179 times 10 to the negative 18 joules. All right, 1 over NF, right? And that would be my final of 1 squared, which is just going to be 1, minus 1 over my initial, which is 6 squared. All right, so negative 2.179 times 10 to the negative 18 joules. This is going to be 1 over 1, which is just 1, minus 1 over 36. All right, so inverse of 36 is 0.0278. If I subtract that from 1, I get a difference of 0.972. And if I multiply that by my constant, I'll get my change in energy. All right, so change in energy. So times 2.179 times 10 to the negative 18. And that negative is still there, right? That negative, whoops, sorry, my computer froze again. All right. So negative, don't forget the negative. Like I said, it's easy to just overlook the negative. So just make sure you know that this is supposed to be negative because we're relaxing to ground state, going closer to the nucleus. So we expect an exothermic transition. So we know our answer should be negative here. So negative 2.12 times 10 to the negative 18 joules. All right, so there's my change in energy for that transition. All right, next question is very similar. We're just going to go in the opposite direction. We want to know that change in energy when we go from 2 to 5. So since we're going in the opposite direction, right, my initial is starting out at 2, my final is going up to 5. We're going to expect here delta E to be greater than 0. We should end up with a positive value here because, again, we're moving away from the nucleus. That's going to be an endothermic change. So same formula, change in energy, negative 2.179 times 10 to the negative 18 joules. All right, 1 over the final squared, 5 times 5 is 25, minus 1 over the initial squared, 2 times 2 is 4. All right, so the inverse of 25 minus the inverse of 4, I get a negative 0.21. And if I multiply that by my constant, all right, now I can see that I've got a negative times a negative, so my delta E is going to become a positive, right? Endothermic, just like we expected. And the answer I get here is a positive 4.58 times 10 to the negative 19 joules. All right, so endothermic versus exothermic. All right, and again, it's because we're moving away from the nucleus. Now, that is our energy of the transition. Now the question says, okay, well, what would the wavelength be? So going back up here to number 10, going from a 6 to a 1, that energy, right? What I could then do is figure out the wavelength of that, because that energy I could relate first to frequency if I wanted to using Planck's constant. And then once I knew my frequency, I could figure out lambda using the speed of light relationship. And so that's what we're going to look at in this last question. So this is where it kind of all tied in for me, is when you look at fireworks and you say, okay, that energy of transition, what I could do is this is relaxing, right? The going from 6 closer to the nucleus to 1. I could take this energy, calculate the frequency, then look at the wavelength and figure out if this is in the visible spectrum. And it turns out, this is another thing I thought was really interesting, is there's something called a Balmer series, B-A-L-M-E-R. And that is that anytime you end, the electron ends in a shell of 2. So your NF is a 2. Wherever it starts from, if that's where it ends, you're going to end up in the visible spectrum. And I just remember being like, how did they figure that out? That's so cool. Like mathematically, how do you, I don't know. Anyway, but again, this is for a hydrogen atom. And again, it's these energy calculations that we do don't work exactly right for every atomic structure. So, you know, but still, I thought when they came up with the Balmer series, right, I just thought it was interesting. Okay, so here we go. We got wavelength for this radiation emitted by a hydrogen atom when the electron is excited from a 1 to a 7. All right, so I would say absorbed, not emitted, unless we're going in the opposite direction. So I don't like that term. We're going to do absorbed. Okay, because we're going in the opposite direction. We're going away from the nucleus. So first thing is delta E, we're going to have our negative 2.179 times 10 to the negative 18 joules. All right, 1 over the final, right? We're going up to, so this one is our final, the 7, so 49, minus 1 over 1, because that's my initial. All right, so inverse of 49 minus 1, I get a difference here of negative 0.980. And if I multiply that by negative 2.179 times 10 to the negative 18 joules, I get a delta E of transition, which is positive 2.13 times 10 to the negative 18 joules. Okay, so we got our energy. Now we want to know wavelength. So first thing is we're going to get frequency by taking E divided by H. So that energy, 2.13 times 10 to the negative 18 joules, divided by the Planck's constant again, right? The 6.63 times 10 to the negative 34 joules seconds. So if I take this and divide it by Planck's constant, I get a frequency 3.22 times 10 to the 15 per seconds. And just FYI, if this energy had been negative, like if we switched it, if we went from 7 to 1, you'll see that instead of negative 0.98, it would have been positive 0.98. And instead of a positive energy, it would have been a negative energy. When you go to calculate frequency, you assume absolute value of the energy because you can't have a negative frequency and you can't have a negative wavelength. So if your energy turns out to be negative because it's an exothermic process, that's fine. But when you go into the E equals H nu equation, just use the absolute value of that energy because again, you can't have negative frequency. So if this had been a negative, that's okay. Just turn it into a positive, divide it by Planck's constant, that'll give you your frequency. And then to solve for lambda, I'm going to say C divided by my frequency. So 3 times 10 to the 8 meters per second for the speed of light, divided by 3.22 times 10 to the 15 per second. So cycles per second cancels out. And whoops, I did that backwards. Let me just type it in again. Hold on, sorry, I hit the wrong key. Okay, got that back. And then inverse times 3 times 10 to the 8. Okay, so 9.3. And my calculator doesn't want to go out any further than that. So I have to be creative. I have to say 9.3 times 10 and then figure out that there's a 4 and then divide it by 10 again to figure out how many zeros. 1, 2, 3, 4, 5, 6, 7. All right, so 10 to the negative 8 meters. All right, so that would be our wavelength. Going back up here, it wanted it in nanometers. So if I multiply that by 10 to the 9, it would be 93.4 nanometers. That would be my wavelength for that energy transition. So not visible for that one if it was going from 7 to 1, but if it was going from 7 to 2, it would be, because that's the Balmer series. Anyway, so in this chapter, there's a lot of calculations, a lot of constants, a lot of math. It's nice. There's formulas. Now, the second half of the chapter talks about the quantum numbers. So I do want to talk about that really quickly, even though it's not on this worksheet. There is in the chapter notes what I did for the videos, because this chapter is pretty short in terms of content, is the first video covers all of these calculations: energies of photons, transitions, wavelength, speed of light, frequency. And then the second video is just about the quantum numbers. So what I was going to do in the little bit of time that I had was just talk about the quantum numbers really quick. So for me, the quantum numbers make total sense if you remember electron configurations back in intro chem. If that isn't the case, it's going to be a little bit harder. The thing with quantum numbers, though, is that we're using, well, we don't really use quantum numbers actually, but you can, I'll put it this way, every electron in an atomic structure has a unique set of quantum numbers. So every electron has its own unique set of quantum numbers. There are 4, all All right. N, which we've already kind of looked at. We saw that with our energies of transitions. This is the principal quantum number. And it's the shell, right, that the electron is in, the energy shell or energy level. I see both terms. So outside of the nucleus, right, where is that electron? Is it in the first shell, N of 1? Is it in the second shell, N of 2, etc.? Then if you remember in intro chem, what we talked about is that within that shell, we can have electrons in specific regions of space, right? They can be in spherical orbits. They can be in those P figure 8 looking orbits or infinity signs, however you want to look at it. They can be like in D where they're between the axes rather than on the axes. And so that quantum number is referred to as L, and that is the angular quantum number. And the rule for L is that L, and I wrote N because that's where my brain was going. Sorry about that. L, the values for L is it starts at 0, it goes up by whole numbers, and what it stops at is N minus 1. Like that's the maximum value for L is N minus 1. So what does that mean? That means that if my N is equal to 1, if I think back to my periodic table, in that first row, right, we only have an s orbital space. If you remember that, this is going to make total sense. So when N is 1, the only value you can have for L is a 0, right? Because we start at 0 and we go up by 1 until we get to N minus 1. And N minus 1, in this case, is a 0. So that's my only value for L. If my N value was 2, and now I'm in the second shell, my L value can be 0 or 1. All right. And if you remember in intro, we had a 1s and then we had a 2s and a 2p. All right. So I think you know where this is going. If N is equal to 3, then your L could be 0, 1, or 2. And that makes sense because we have a 3s, a 3p, and a 3d. And if N is equal to 4, L can be 0, 1, 2, or 3. And that's because we have a 4s, a 4p, a 4d, and a 4f. Now, theoretically, we have higher values for L, right? We can go L of 4, but on our periodic table, we don't have anything past an F, right? Maybe one day, but not anytime too soon, I don't think. So your L, your angular quantum number, are those spatial arrangements, right? Are the electrons traveling in a spherical orbit? Are they in that figure 8 pattern of a p orbital? Are they on the axes or are they between the axes? Between the axes like they would be in a d orbital. So that's what the L is giving us, is whether you have S, P, D, or F. So when your L is equal to 0, that is an S space. When L is equal to 1, that's a P space. When L is equal to 2, that's D subshell. And when L is equal to 3, you're looking at an F subshell. All right, so those are the values possible for L. All right, so principal quantum number, angular quantum number, there's more. Now remember, when we were within the subshell, we could hone in on specific orbitals. So we have M sub L, which is the magnetic quantum number. And I don't know if we need to remember the names. Like they don't necessarily make a ton of sense. Like why couldn't they call that like the orbital quantum number? Like then it would be like, oh yeah, that makes sense. Now the values for M sub L, what you have for M sub L is M sub L can be negative L through 0 up to positive L. And again, moving in whole numbers. So if, for example, L is equal to 1, that means your M sub L could be negative 1, 0, or 1. So remember when we had an L of 1, we were talking about a P subshell. And if we remember intro chem, when we did our P orbitals, we drew 3 P orbitals, right? There were 3 boxes. And that's because when we have our P orbitals, right, we have 3. We have one that travels along the x-axis, one that travels along the y-axis, and then one that's out on the z-axis. And so there's my -1, 0, and 1 for my 3 possible orbital values. So the M sub L is taking that sublevel and looking at the specific orbitals within that. So if L is equal to 0, your M sub L, the only value there is 0. And that makes sense, right? Because with an S, right, if you remember, we only drew one box, right? There's only one orbital space. And so that M sub L value there would be a 0. Now, the fourth and final quantum number is your spin, and it's M sub S. All right, that label made sense to me, the spin quantum number. And if you remember, inside an orbital, when we paired electrons, we gave them opposite spins, right? One up, one down. And that is because we want the electrons, they repel each other, which is a destabilizing force, right? That makes them unhappy. So if they can be rotating in opposite directions, that counteracts that repulsion just a little bit. So we show them spin up, spin down, and that helps them partner up just a little bit, right? Now, the M sub S values, they are either going to be plus or minus 1/2. All right. I don't know why a half. I've never seen the historical reasoning for 1/2, but okay. So if I look at any electron in an atomic structure, it will have a unique set of quantum numbers. It will have the shell that it's in, the N, the principal quantum number, the subshell, whether it's SP, D, or F, that's the angular quantum number. Within that subshell, what orbital is it in, right? That's the magnetic quantum number. And then within a specific orbital, what spin does it have? Plus 1/2 or negative 1/2. So those are your quantum numbers. A lot of times what they do when they introduce quantum numbers is just kind of ask you what set of quantum numbers is possible. So like as an example, if you were given an N of equal to 4, an L of equal to 3, an M sub L of 0, and an M sub S of 1/2, is that a possible set of quantum numbers? And the answer would be yes. Because if N is equal to 4, the max value for L would be 3, right? This right here is telling me I have a 4F sublevel, and that's doable. Your M sub L values can be anything from -3 to +3, going up by whole numbers. So 0 is right in there. And then M sub S could be a +1/2 or a -1/2. So yes, this is a possible set of quantum numbers. If I change it and I said, okay, let's say you have an N of equal to 2, L is equal to 2, M sub L equal to 2, and M sub S equals to 1/2. What I look at here is L is equal to D, right? Remember, 0 is S, 1 is P, 2 is D. And the rule with L is that the max value is N minus 1. So if N is equal to 2, the max value I can have for L is a 1. And we know when we look at the periodic table, there is no 2D subshell, right? So this one is not okay. So that's a lot of what you do when you learn the quantum numbers, is just kind of understand what the possible relationships are. And so hopefully I've made that clear either here or in the video for the notes, just kind of talking about, okay, your principal quantum number can really be any whole number, right? And I mean, our periodic table goes up to 7, but it could go up higher than that. Theoretically, there's room for more. The angular quantum number, that subshell, right? Even though our periodic table only goes up to F with an L value of 3, again, theoretically, there's room for more. But the rule is that L maxes out at N minus 1. So if you're given an N of 1, the only L you can have is a 0. If your N is 2, L could be 0 or 1. Your M sub L values are the orbitals within that subshell, and they have values anywhere from -L to +L. Those are possible. So if you had an L of 2, your M sub L could be -2, -1, 0, 1, or 2. And then the spin makes sense. It's just +1/2 or -1/2. All right, so that is chapter 8. There's no credit quiz for chapter 8 because the next thing on the agenda for next week will be test 2. But there are practice quizzes to help you practice the material. I did my homework. I'm going to scan and post that tomorrow along with the answer key to the worksheet. So there's not as much to do with chapter 8, but I feel like that's probably a good thing to help us get a little bit of time preparing for the test that will be next week, due next week. The chapter 7 credit quiz, well, it's the 6th credit quiz, but for chapter 7, that's due today at midnight. I will get that graded hopefully tomorrow, Thursday at the latest. And then next week, the focus will be the test. So next week's Zoom session will be a review for the test. I think that'll be a good place for me to stop for today.